Okay, hello again, Year 10. Welcome to the third video then, and we're moving away from momentum now, moving on to look at energy. And so really through this topic we'll be looking at some of the different formulas to do with energy and how you do questions. So the first thing then, and the title of this video is work done. Now, I'm not just talking here about how much you've been doing while we've been on lockdown. Work done is actually an official term in science, and it is just to do with energy. And so, like with all the videos, it would be a good idea if you were writing down the things that I'm putting on here into your books. Work done just means the following. Okay, so work done means energy transferred by a force. Okay, it's as simple as that. So when you see that phrase work done, it's just meaning energy transferred. And so, like you might expect, if it's energy, it's measured in joules. Because it's energy, energy as we know is measured in joules. Now you have actually come across the phrase work done before. Back in year 9, when you first talked about energy stores and transfers, we talked about energy being transferred by mechanical work, in other words by a force. And that's just this idea, work done, energy being transferred by a force. Now it's got quite an easy formula. Okay, another one which shouldn't cause us too much trouble. So work done equals force times distance. Now, the only thing I want to just make sure is that this distance, it is the distance moved in the direction of the force. Now, I will show you this in more detail when we look at some examples in a minute. So it's the distance moved in the direction of the force. But checking our units then, work done, well, we just said that, it's joules. Force, as you hopefully know, measured in newtons. Distance, measured in meters. Okay, and that is all there is to it in terms of the formula. If you want it as a formula in symbols, again, I don't recommend you use them, but if you want it, work done, capital W, force times, now distance, if you remember back to motion, distance is given the letter S. Now this is why I recommend not using the symbols, because if a question said, write down the formula for work done, if you wrote down W equals F times D for distance, there is a chance you might not get the mark. So if I were you, it's not a very long one to write down, I would just write it down in words. Right, it's example time. So you can see here I've drawn a very not to scale drawing. This is actually a ski slope, and it's 500 meters long, the actual slope. But the vertical height that you move down as you go down those 500 meters is 50 meters. So if we imagine then we've got a person skiing, okay, here they are, I'm not sure how well I'm going to be able to get them to stay there, they might have to lie a bit like that. They'll ski down, okay, down the slope. Now, what I want to do is just look at a couple of examples of this, and let's just move our skier up there. Okay, and I want to just add on a little bit of extra information actually about our skier. So let's say that our skier has a mass of 60 kilograms, and I'm going to say that there is a friction force of 0.5 newtons. Well, that's actually very, very small, but you know, he's on snow, there wouldn't be a huge amount of friction. And so I'm saying my friction force is 0.5 newtons. We're going to look at two examples here. Okay, as if by magic then, there's question 1. Find the work done against friction as he skis down the slope. So I'm going to go to my formula, which is the same as we wrote just up there. Work done is force times distance. Now we're talking about friction. Now friction, if you think about which way the friction is actually going to be acting, this is going to be quite difficult to draw. Let me just take our skier off for a second. The friction is going to be acting along the slope, so in the direction of that red arrow there. I know that's not particularly clear, As the skier skis down, the friction's acting along the slope. So the force I want, well, that's going to be my force of friction. The distance moved in the direction of the force. The friction is along the slope. We want the work done against friction. So the distance being moved there is 500 metres. So that gives me an answer of 250 joules. So that means as he skis down the slope, friction is transferring 250 joules of energy. Where's that energy going? You might be thinking, well, energy's got to be conserved. Where has that gone? And actually, in the case of friction, friction causes things to heat up. And so that 250 joules is going to be transferred to the thermal energy, ultimately, of the surroundings. Okay, now you know that this is the case. You know friction makes things get hot. If you rub your hands together, they will get hot. And that's because work is being done. Energy is being transferred, and so your hands end up heating up. And now you also know that actually if there was a lot more friction, a lot more energy would be transferred. And it's a good job really that this is the case, because that's how brakes work. Think about brakes on a bike, in your car. There are pads and discs. Friction happens in the brakes when you apply the brakes, and that transfers energy into thermal energy. Brakes get really, really hot, and the more friction there is, the more energy gets transferred. Okay, so for example 2 then, what we're going to do is we're going to imagine that our skier here, he's got to the bottom, and he's going to get on the ski lift that takes him all the way back up to the top. And so what I want to do this time, is to find the work done against gravity as he climbs back to the top. Okay, now, again, work done as force times distance. That's not too bad. We do, though, have to be really careful here, because we're looking at gravity. And so force times distance, well, we don't have a force. We don't have a force of gravity. Now, I'm hoping that you can remember how we find the force of gravity, or rather, first of all, another word for the force of gravity on an object. Hopefully, you can remember that weight is another word for the force of gravity on an object. So we need to start off then by working out the weight. All right, so our mass is 60, we need to work out the weight. So I'm going to just move down here to do this. I might need to just hide our formula for a second. Hopefully from earlier on in the year, you can remember the formula for weight. If not, it's a good chance to revise it. Weight is equal to mass times gravitational field strength. Okay, mass then is 60. You remember what gravitational field strength is on Earth? Hopefully you can. It's 9.8 newtons per kilogram. Okay, so 60 times 9.8, that is 588 newtons. So my force, my weight is 588. So let's just bring this down to here then and carry on with our calculation. So work done equals force is 588, because that's the weight, that is the force of gravity, times the distance. Well, the distance moved in the direction of the force. Remember, gravity is downwards. Okay, it's a vertical force. So we're looking at this distance moved up and down. So in this case, against gravity, so moving up. And so it's moved 50 meters up. 588 times 50 gives me an answer of 29,400 joules. So that's how much work is done, probably by a ski lift, to be honest, in moving that man back up to the top of the ski slope. Now again, you might say, well, where has that energy gone? Okay, it's being transferred by mechanical work, but where? Where has it gone to? Well, it's got higher up. Okay, so it's going to be transferred to gravitational potential energy because that person is getting higher up. And in a future video, we'll talk a lot more about the idea of gravitational potential energy. Okay, that's pretty much it then for work done. Hopefully that will allow you to answer some questions on work done. As always, if you've got any feedback, any questions, feel free to drop me an email. Otherwise, stay safe. I'll see you on the next video where we're going to talk about power.